So in this video we'll discuss about the realization of digital filter. So if we take the digital filter, I can classify into two types. One is a recursive type, and the another one is non-recursive. Means that it is in the recursive type, the output is dependent on past input and output and present input. And in case of the non-recursive filter, it is dependent on present and past inputs. So essentially this becomes an finite impulsive response filter, and this becomes an IIR filter, infinite impulse response filter. Okay, so now whatever the type of filter, now let us consider this IIR. This one. So far we were discussing about the IIR filter, its implementation. So it can be implemented in many ways. So let me take it direct form 1, direct form 2, cascaded form, parallel form, lattice ladder structure. All these things are classified based on how a filter is really implemented using a DSP hardware. Okay, so based on the DSP hardware, how it is realized. So this based on this only it has been. So here on what are all the things that has been considered here is the number of delay elements, number of memory elements, number of adder, number of multipliers. So on what why we are considering all these things here is, again, if you take an expression of an system, that is output of an system y of n, it is represented by some a1 x of n plus a2 x of n minus 1 plus a3 x of n minus 2 plus b1 y of n minus 1 plus b2 y of n minus 2, and so on. So if I combine, if you see this, here I need a multiplier. I am multiplying two terms, so I need a multiplier. Now these two product terms are combined using an, are added together, so I need an adder. And if I see this particular element x of n minus 1 means x of n delayed by n, delayed by one sample, means that the previous sample of x of 1. So I am considering this as an equivalent to an delay, or I can consider this as an memory. So like this, how many elements I need for the realization of the filter is going to give you this classification. Okay, so what we actually need, so far we designed h of z. What is h of z? The transfer function of the filter, which is nothing but the ratio of output to the input. Now how this is been represented? This is represented as summation k equal to 0 to M bk z power minus k divided by 1 plus summation k equal to 0 to n ak z power minus k, provided that provided I have this n greater than or equal to m. This is the condition I am taking it. Okay, and what we need on the, but if you take this our realize in to have this in a realizable format, I'm just going to make a slight alteration to this equation. So let me take it y of z into 1 plus summation k equal to 0 to n a k z per minus k is equal to x of z times of summation k equal to 0 to m bk z per minus k. Okay, and since this summation is in with respect to k, what I can take here is I can take this inside y of z and x of z inside this parenthesis. So I can write y of z plus summation k equal to 0 to n y of z ak z bar minus k is equal to so I can write here as summation k equal to 0 to m bk x of z into z bar minus k. So now on taking inverse that z transform, we have this y of n plus summation k equal to 0 to n ak y of n minus k is equal to summation k equal to 0 to m bk x of n minus k. So from this what I can write here is y of n is equal to minus summation k equal to 0 to n ak y of n minus k plus summation k equal to 0 to m bk x of n minus k. Okay, so in this way only this y of n is being taken. Now how this expression is realized in a hardware? How this is realized in hardware, that is our task. Okay, so let me take it for the first one. direct form 1 realization. So in the direct form 1 realization, let me consider this. Okay. So let b naught x of n b1 x of n minus 1 plus b2 x of n minus 2 and so on up to bm x of n minus m is equal to w of n. Okay, so from the in the actual expression I'm going to write it in this way, and so I can therefore y of n is equal to minus a1 y of n minus 1 minus a2 y of n minus 2 minus a3 y of n minus 3 and so on up to minus an y of n minus 1 plus w of n. Okay, so let us take this, how I'm going to derive this w of n and how I'm going to derive y of n. Now if I take this w of n, it comprises fully of the input samples x of n, x of n minus 1, x of n minus 2 up to x of n minus m. And if I consider this y of n comprises of the delayed samples of the output y of n minus 1, n minus 2, n minus 3 and so on y of n minus 1 plus w of n. Okay, just the same equation, a single equation now split it into two equation and we are going to implement it step by step. So let me consider how I'm realizing this w of n. So what is w of n? b naught times of x of n plus b1 times of x of n minus 1 plus b2 times x of n minus 2, like that. Okay, and before that let us understand one thing here, the convention, how we are going to make it on this one, that is how I'm going to pictorially represent all these things. So if I consider a line, let this be the input and let this be the output y of n. If I have an arrow here which indicates the direction in which the signal propagates, and if I'm indicating a constant over here, let us say n a constant, whatever it is, what it means y of n, the magnitude of y of n is equal to a1 times of the input x of n. Okay, and then if I have an block like this, x of n, and it produces an output y of n. So this y of n is nothing but x of n minus 1. This is represented as an delay element. Okay, and similarly if I have an circle inside summation and it is going to have two signals x1 and x2 and it is producing an output y as x1 of n plus x2 of n. So we are going to use these three notations only repeatedly for implementing whatever the functions we want to realize. Okay, so let us implement w of n. So if I take it, let me take this as x of n. I have this b naught. So what I have here is b naught x of n. It can be plus symbol or whatever summation symbol you can use. W of n. Now to this I need to add, I'll be adding one delay element. So here I'll get x of n minus 1. This should be multiplied by b1. So let me have an adder here. Okay, so let me have one more delay element. To this delay element, the input is x of n minus 1. So it will produce an output of x of n minus 2. So this should be multiplied by b2. Okay, so it is added up then. So what I have here, I'll be having b2 x of minus 2, and here I'll be having b1 x of n minus 1. So at this point I'll be having b1 x of n minus 1 plus b2 x of n minus 2, like this. Like this, I'll have m delay elements here. Let it keep on. I'll be having on final z bar minus 1, where my output is x of n minus m. This is multiplied by bm adder. Okay, so I can combine this over here. So how it will be modified? Here up to and so on up to bm x of minus m. So this is my w of n realization. In the similar way, I need to express this one, y of n. I wish to implement this y of n. So now if you see this y of n, the similar way I'm going to realize this for y of n. So for y of n is, let me take it. So let me write the equation first here. Y of n is equal to minus a1 y of 1 minus 1 minus a2 y of n minus 2 and so on minus an y of n minus n plus w of n. Okay, so let me take this w of n already we synthesized, w of n added with, okay, so I'll have this to be y of n. To this if I add one delay, I'll get y of n minus 1. If I add one more delay, I'll get y of n minus 2 and so on. I'll have it. If we had this last, the nth element, then I'll get y of n minus 1. Now what I'll do, I'll be having an adder here, and this gain I'll keep it as minus a1. Okay, so here if we take it, I'll have an adder here, y of n minus 2, so minus a2 y of n minus 2 minus an. So here at every point, if you take it, it will get added up. Will realize an filter. Okay. The next step, what we need to do is we need to combine both your that is uh, implementation of this w of n and then this y of n. These things should be combined. How it is done? Okay. I'll keep this sum w of n x of n is written as, and similarly b naught b1 b2 bm, right? So we'll add it. And then this part we have to take it here. From w of n to y of n, I need one more adder. Y of n so if I have this minus an. Okay, so this is the realization of filter, a digital filter, IIR filter using direct form 1. Now if you see this, how many delay elements we needed, how many multipliers we needed, how many adders we needed. So if I take in this case, I'll be requiring totally m plus n plus 1 multiplication, m plus n plus 1 multiplication, and then I'll be having uh, m plus n addition, and I need m plus n plus 1 memory location. Okay, so this is the feature of an direct form 1 realization. So since it needs this much number of memory location, multiplication and addition, I feel realizing this in a hardware is a quite difficult task, or it may be an it consumes more hardware requirements over here. Why can't we minimize this? So in order to go with this, we'll considering the direct form 2. Okay, so this direct form 2, again we are going to make a slight modification in this.